Okay, now it's time to start part 3 in the radar antenna lecture in the Introduction to Radar Systems course. Okay, now let's move on to phased array antennas. Okay, what are phased array antennas? Well, first of all, let's look at these gain patterns. And these gain patterns are in dB on the y-axis as a function of angle. And we have let's say we have an isotropic element. It's uniform across all. Now, say for instance we take an array of elements. It could be isotropic, or it could have a little bit of directionality like a dipole. And we combine them. And we just combine them. And remember what we did when we, well, we'll see in a minute when we combine them what happens. What happens is that the phases, the amplitude and phase of this radiation will constructively and destructively interfere with its neighbors. And what you'll get for a gain pattern when we just sum them, we just add them together, is we get a gain pattern that has a maximum in the center. And I'll just say as a caveat that the distance between these antenna, these little elements, we'll call them, elements of an array antenna, this distance is less than half of the wavelength of the energy we're radiating. And what we get is one big bump. If we take, let's say they're half a wavelength apart. So we've got like a wavelength and a total of a wavelength here. And then we move the, here we have 1, 2, 3, 4, 5, 2.5 wavelengths they are. You see that the width of the beam gets narrower and the gain gets higher. This is relative response. When we take, so what happens is when we add them all up, we get, if we add the gain from 3, we get more gain and we get some directivity. Broadside, when we're looking straight out. If we just add them and we add more, we get a lot more gain and a lot more directivity, and notice the side lobes go down. Now, if we can adjust the phase of these different elements, the emissions from these elements, so that at one point in space, one angle away, they all add up constructively, and we get the same constructive interference, which gives us good directivity and narrow beam width at a different direction. If we appropriately shift the phase of all these different elements. Now, what if we could do that very, very, very quickly? We could change the direction that the antenna was pointing very quickly. Now, I'm going to steal my own thunder. People decades ago invented ferrite phase shifters that could shift phase at high power in microseconds. Imagine that big antenna that we just, I'll go back to it for a minute. That big antenna. Say it's pointing up in space in one direction. You wanted to move that antenna 30 degrees or 20 degrees over in space. Big motors. You can imagine the inertia in that antenna to do that. Enormous job. Enormous job. But if I could have this antenna face be a whole raft of, a whole face of elements, and I could just change the phases in microseconds, that beam could be pointing over in another direction microseconds later. And that could allow me to flit back and forth the beam. Okay, that's a neat idea, and that's we're able to do that with today's technology, and that's called phased array antenna. Okay, now let's see how the phasing works for the constructive interference and destructive interference. Here, just for simplicity's sake, we're going to take the two dipoles separated by many wavelengths, and we're going to have them transmit. And remember, red is where they're constructively interfering. Here's the main beam, And what you see is the main beam, and then a minimum, and then a maximum, and another. And so we see side lobes that are pretty sizable, by the way. And this is a typical interference pattern. Now, if I move, these are called grating lobes. If I move these dipoles close together, which I haven't done in the animation, and I move them real close together, like about half a wavelength or less, approximately half a wavelength, those grating lobes will disappear and I'll just see one main beam. And if I had a whole row of dipoles and I shifted the phase, that one main beam here, I could get it to point just one beam in that one direction only. And that's what phased arrays are and how they work. So let's look at controlling arrays. Yeah, and how the array, controlling the phase on the different elements, allows us to keep the wavefront so they constructively appear. So let's just say we have an element, n elements separated each a distance d from each other, and there's a wavelength lambda involved in here. And we can see, now if I want the radiation to all be in phase at a certain scan angle, then what I have to do is adjust the phase. I can set arbitrary phase, say the first one, but I have to set the phase of all the remaining elements such that I have a maximum out in the far field along a line, along that plane wave in the far field. Okay? So that's what I need to do, is make those phase adjustments. And as I've said, we now have technology that allows us to make those phase shifts electronically. Just go switch. A few microseconds later, the phase is a shift, and where the antenna is electrically pointing to receive or to transmit has been changed. Change it again, microseconds, it's pointing in another direction. Okay? So we have lots of different geometric configurations we can make these phased array radars. We can, for the elements, we can set them along a line, rectangularly, in circular grids. And there's a whole book written, well, a couple of different books written on how you design phased array radars. Another parameter to deal with is the element separation, the phase shifts, the amplitudes, how we amplitude modulate as we go down the array. That will control the side lobes. And the pattern of the individual elements. Are they dipoles? Are they isotropic elements or special design? All these parameters will go into the design of the exact performance and directivity and side lobe level of a phased array radar. But we're just going to go into some of the basics here. Okay? First of all, let's look at a linear array, just along a line. We'll worry about 2 dimensions later in the end. Now, first what we have here are 10 elements, all in the z-axis, vertically. And we have, here is the shape of the main beam and the side lobes. And here we have, and this here we show, this would be on a linear scale, but right up here is on a dB scale, where you see the side lobes, and you can see the side lobes, the gain is, this is 10 dB above isotropic, and 0 is this is the gain above isotropic. We have 10 elements, so the elements all add up constructively. If we make, and for this case we're looking at lambda over 2 separation, that is the spacing between elements is a half a wavelength. We're doing no phase shifting at all, and we just got isotropic elements. Each element transmits isotropically in all directions. And when we look out perpendicular to the line of the array, that's called a broadside array. This is a linear broadside array. We're going to look at what happens when we increase the number of elements in the array. We get, as we double the number, we get double the gain. 13 dB is double 10 dB. And we double it again to 40 elements, we get 16 dB. And notice the side lobe level, way down in the lower side lobes, goes down. So the gain for a long broadside array is twice the number of elements times the spacing divided by lambda. And if d is lambda over 2, then the gain is just the number of elements. Simple. Long linear elements, 10 elements, just take the its factor of 10 is the gain. Logarithm to the base 10 of 20 is 2 times 10. Is 1.3 times 10 is 13 dB. And the same here. The logarithm to the base 10 of 40 is 1.6 times 10 is 16 dBi. So you can see just that's the gain. Okay. Now let's move on. Again for a broadside array, and let's look and see what happens if we change the separation. If we make the separation lambda over 4, we just get a gain of 7 dB above isotropic. And if we get a gain, if we separate them lambda over 2, we get the full gain of 10 dB. But if we separate them more than lambda over 2, in this case if we separate them a wavelength, so-called grating lobes appear. And that means that significant amount of energy is received at angles other than the beam, the angle we want to point at. In this case directly, we're looking broadside, we're just looking broadside, but we'll receive energy out at 0 degrees and 180 degrees from it. So we'll receive energy with equal sensitivity here and here with separation of lambda. We don't want grating lobes. Grating lobes are a no-no. Okay? So to limit, for a broadside array, to limit element separation to less than lambda will prevent grating lobes. Now if we look at an end-fire array, and an end-fire array is one where it's our main direction that we're looking is along the direction of the elements, and that's called an end-fire array. So for an end-fire array, and it's phase shifted, we've already got the phase shifters shifted so the beam will point up. And now we say, what does the gain pattern look like for this end-fire array? For 10 elements. In each case, it's just 10 elements. For lambda over 2 separation, for lambda over 4 separation, we see we've got a decent beam at 0 degrees. At lambda over 2 separation, the grating lobes appear. And at lambda separation, grating lobes appear. So when we're operating an array in end-fire mode, then we need the separation. There are no grating lobes for separations between d and lambda over 2. And the gain is 2L over lambda for a long end-fired array without grating lobes. Okay. So if we have a linear phased array, what happens when we scan? We've just been looking at all those previous patterns, and when we were looking just broadside. What happens if we set the phasors up to point the beam off of broadside with a broadside array? Well, first of all, here's let's say broadside. Here's our set of elements, and right here, relative to the vertical, the broadside direction would be out this way, which would be 90 degrees. So here's that broadside gain pattern, and we see it's all nice and fine. We've got a nice, well-defined beam, reasonable side lobes. If we shift it out 30 degrees to the angle, we see that the beam broadens. And if we shift it out 150 degrees, broadens even more. And if we shift it out 90 degrees, we get it broadens a lot. So the beam width increases as we scan off broadside. So to scan over all space without grating lobe, we want to keep the element separation at less than lambda over 2. That's an important thing. Okay? And for this is a case where we scanned every 30 degrees with 15 elements and the separation was lambda over 4. But the bottom line here is, don't make your separation elements greater than lambda over 2 if for all space you don't want to see grating lobes. Now, this broadening is an important factor, and you lose resolution. So a lot of the time, people don't want to scan more than 45 degrees because they don't want to lose angular resolution. And that'll allow you to go like 0.7 lambda. You know, not lambda over 2, but 0.7 lambda for your spacing. Okay? Now, one other thing I want to point out is that the gain drops with the cosine of your broadening angle. Now, like, the gain goes down with the cosine of your beam off of Broadside, and the beam width increases by when it'd be your baseline beam width divided by the cosine of the angle that you're off of Broadside. That's just a little tidbit I'll add in. Now, what do you do with planar arrays? Well, here we have it right here. Excuse me. With planar arrays, it's just adding another dimension. A planar array is just an array of linear arrays. And here is the pattern you get in 3 dimensions with spacing of lambda over 2 and with 5 elements. And as we scan off a Broadside, say theta 0, as I just said, the beam width broadens by 1 over cosine of the scan angle, and the directivity, the gain, decreases by the cosine of that scan angle. And again, for a planar phased array, to scan over all space without grating lobes, keep the element spacing, separation, in both directions less than lambda over 2. And my rule of thumb when I'm thinking about designing antennas, because of that broadening effect, you can get away with 0.7 lambda when I do my radar phased array designs, because you don't want to suffer the kind of beam broadening and directivity decreasing if you go out more than 45 or 50 degrees. That's a trade-off in the radar systems design, though. This whole business of what happens when we take a set of elements and put them along a line all assumes that one element, that the effects that we see in the far field and in the near field and everywhere, one doesn't affect another. And how we design that antenna is what the patterns of each element are independent of any other elements nearby. And that's not true, because Maxwell's equations have to be satisfied everywhere. And as an element is generating on the surface, on that dipole currents, those currents generate fields nearby and induce currents on nearby elements that are like lambda over 2 apart. So the coupling that they have between one and another, they don't act completely independently. And that's a near field entity. It affects one another. And the design of the pattern is such that you have to take these mutual coupling effects into account. And it has an effect on the input impedance that the system sees. And it also depends on scan angle, because you can understand that as you scan the antenna so the radiation is pointing more in one direction than in another, then it's going to affect the currents that are induced in the nearby antennas. So the impedance effects are going to depend on how you scan. The mutual coupling effects are going to. So this is a complicated. I like to say this is something that's really, if you go to many of the solid introduction to Merrill Skolnick's Introduction to Radar Systems book, even for those, we don't completely understand mutual coupling. It is an art form. You can get mutual coupling in antennas that some people say you can get a scan blindness where no power is radiated. You can see this when you do the design with modeling, but when you go, there's modeling and the models and the analytical calculations are always based on the reality, and then you go measure it and you get different things. This is what people, professionals, the antenna designers, write professional papers on these days. The point I want to make to you newbies to the world of radar and antennas and phased array antennas is that mutual coupling is an effect that you have to take into account. The expert radar designers will. It can limit the scan volume and the array bandwidth, and it sometimes can be exploited to get performance requirements, to achieve certain requirements. And one element doesn't act in independence of another. And for the relative neophyte to the radar world, that's the important thing you need to take away from this last minute or two of view graph and words. Okay, now I've talked about phased arrays, I've talked about reflectors. What do you do? Look, if you've got the job to track one target up in space, you want relatively high power on it, a dish antenna is usually the way to go. You don't need a phased array. And there is some, and you can get away with the lowest cost. If you've got an operational requirement where you have to track a lot of targets simultaneously at a lot of different angles, you're either going to have to buy a lot of dish radars, because they can't go back and forth mechanically that fast. You're going to have to build phased arrays or use other, I haven't gone into other modes of scanning other than phased arrays and reflectors. There are antennas that scan with frequency shifting, which is another topic, don't have the time in this lecture to go into that. But phased arrays, to contrast phased arrays and reflectors, they provide beam agility and flexibility. You can do multiple functions. You can have a set of beams that are doing surveillance down at the horizon, and at the same time you're tracking targets way above the horizon. So you can do near simultaneous tracks over a wide field of view. The next major bullet, gets into it. It's expensive. It's more expensive to build a phased array with the same power aperture product as a reflector. But if you need 360-degree coverage, you may need 3 or 4 filled array faces to cover that. Because I mentioned, you can't scan the phased array 180 degrees and have 2 of them back to back, because you'll have scan losses and the beam shapes will be very poor out at the wide angles. So you're going to have multiple phased arrays to cover 3 or 4 filled arrays to cover 360-degree coverage. There's a larger component cost. I alluded to earlier, no, not yet, it's in a later lecture, in the transmitter lecture, and you'll see that the cost per element can be quite high when you add up getting the same power aperture product out of one big transmitter versus a lot of transmit-receive modules or a big phased array antenna. So it can be larger costs, and they're significantly more expensive. They can be. And it can be a longer design time, too. Dish antennas are much more off the shelf and much easier to build from an engineering point of view. But many requirements that the government require the technology that are within phased arrays, and thank God we have them, are able to perform very complex missions that some different radars require. It's a trade-off, as they say. Okay, now to summarize. Covered an awful lot of material, and I'll probably be breaking this up into 3 pieces, not just 2. Okay. Now, in summary, we've talked about antennas, fundamental antenna parameters, and of array antennas. The topics we've discussed are the radiation, gain, pattern, side lobes, bandwidth, polarization. We've talked about the far field, a little bit about the near field too, input impedance, how we form beams with arrays. We talked about mutual coupling. For reflective antennas, we talked about parabolic feeds and Cassegrain feeds as relatively expensive ways to get high gain on an antenna that wants to look generally at one time at one place in space, and that can very slowly go over and then with a mechanical scan relatively slowly go over and look at another place in space. And phased array offer the beam agility and flexibility, but they're much more expensive than a reflector antenna. And as I mentioned also, there are other kinds of antennas that use frequency shifting to do scanning. And then radars also can be hybrids of phased arrays, where you can have phased arrays for one dimension and mechanical scanning in another direction, or frequency scanning in one dimension and mechanical scanning in another. So you can build hybrids of them. And what I want to just let you know in ending is that it's a very rich topic that we probably could spend double the time we've spent on it. And this gives you the basics, and it does more, I hope, than scratch the surface, but gives you those basics so that you understand the basic concept of antennas that are used in radars. Thank you very much. Hello. Now we'll start part 2 of the radar antenna lecture, and it's lecture 6 in the Introduction to Radar Systems course. Okay, now it's time to start part 3 in the radar antenna lecture in the Introduction to Radar Systems course.